Quantum computing is on the brink of a breakthrough, but only if we stop waiting for perfection. Most quantum systems today are like tiny, fragile sparks, promising but too weak to power real-world applications. But what if you could build a fire by linking those sparks together, even if the connections between them were shaky? That's the core idea behind a groundbreaking study from the University of California, Riverside, which reveals how to create scalable, reliable quantum computers using existing imperfect hardware. And here's the twist. Even with noisy, error-prone links between chips, the system can still function and even outperform expectations. The challenge has always been scaling. Quantum computers rely on qubits, the quantum equivalent of classical bits, but these qubits are notoriously unstable. To make them useful, scientists bundle hundreds or thousands of physical qubits into a single logical qubit, which acts as a more reliable unit. This redundancy helps correct errors, but until now, connecting multiple chips, each with their own clusters of qubits, has been a major hurdle. But here's where it gets controversial. What if the solution doesn't require flawless connections? What if good enough is actually good enough? The UCR-led team simulated various modular quantum architectures and found that even when the links between chips were up to 10 times noisier than the chips themselves, the system could still detect and correct errors effectively. This means we don't need to wait for perfect hardware to build larger quantum systems. Instead, we can start now with what we have and iterate from there. This is the part most people miss. The study doesn't propose new chip designs. It's about rethinking how we connect existing components to create something greater than the sum of its parts. As lead author Mohammed A. Shalby explains, it's a foundational shift in how we build quantum systems. Fault tolerance, the system's ability to self-correct errors, is key. In classical computing, redundancy is straightforward, but quantum systems face unique challenges. For example, connecting chips housed in separate cryogenic refrigerators introduces noise that can disrupt error correction. Yet the simulation showed that as long as each individual chip operates at high fidelity, meaning its internal qubits work reliably, the system can tolerate noisy links. This opens the door to modular quantum architectures, where smaller chips work together like a distributed network rather than a single monolithic processor. The team tested 6 different modular designs using parameters inspired by Google's existing quantum infrastructure. They focused on the surface code, a widely used error correction method that encodes logical qubits by managing errors within the chip's architecture. By optimizing these surface code interfaces, they demonstrated that scalability and reliability aren't mutually exclusive. In fact, the study argues that focusing solely on increasing the number of qubits without addressing fault tolerance is like building a house without a foundation. So what does this mean for the future? The implications are huge. If we can build fault-tolerant systems today, industries like drug discovery, cryptography, and materials science could start leveraging quantum computing far sooner than anticipated. But here's a question for you. Should we prioritize incremental progress with current technology or wait for flawless hardware that might take years to develop? Share your thoughts in the comments, because this isn't just a technical debate. It's a philosophical one about how innovation should unfold. The research was co-authored by Leonid P. Pryadko and Ren-Yu Wang at UCR, along with Denis Sedov from the University of Stuttgart. For more details, read the full study in Physical Review A, DOI 1103 XQRN WDW1, or explore the preprint on archive.2503.04968. And remember, the next time you hear about quantum computing, Ask yourself, how much of the magic is in the hardware and how much is in the way we connect it?